All right, let's cover the unit step and some Laplace transform stuff involving unit step. Here's how we'll define it. The subscript U stands for unit step. T minus A is the argument, which means it's 0 where T is less than A and 1 where T is greater than A. What exactly happens when T equals A is not that important. Different textbooks define it different ways. Here's what it looks like. It's 1 for T greater than A, 0 for T less than A. If there is no little a here, if it's just U with an argument of T, it starts at 0. It's 1 from 0, T equals 0, all the way up to infinity, and 0 to the left of 0. What if we had a function and multiplied it by unit step T minus A? Well, since it's 0 to the left of T, it just lops off function everything to the left of A. So our new function is this thing. It starts over here. It's this original function, just you lopped off the left side of it. What if we time shifted this function? You'd shift to the right by subtracting off A. We shifted A units to the right on the timeline, or the real line, by subtracting off A. So F with the argument of T minus A looks like this guy, but he starts at A instead of 0. So he looks like that. Let's see what, well, so I could shift the whole thing to the right by this, changing the argument of the F, and then multiplying by the unit step at the same argument, T minus A. That ensures that even if there were something to the left of 0 in the original function, it's going to get lopped off when we multiply by U of T minus A. Because generally we think of our function starting, there's 0 to the left of 0, but just to ensure it, we'll multiply by the unit step. So what is that? What is that? What's the Laplace transform of a shifted function, and we make sure it's 0 to the left of that little a? I'll put it in the definition of the Laplace transform. This change, let's see, we'll do a change of variables. Comes this, and we can pull out an e to the minus as. And what's left inside the integral is the original Laplace transform. So that time shifted function, if I time shift a function to the right by a units in the time domain or the t domain, in the s domain, it means multiplying by e to the minus as, the original Laplace transform. So this is a property we would add to our Laplace table of properties and pairs. What about the Laplace transform of just the unit step itself? Well, I can consider that as the unit step times the function 1, which is by this property then would have this Laplace transform, and that was 1 over s, so it would have this. This is the Laplace transform of the unit step. And if it's just a unit step, the argument of t rather than t minus a, it's just good old 1 over s. Same as the Laplace transform of 1. Way back in our, I think the first recording of the Laplace transform. What if I, instead of the time shifted version of the original function, I just cut it off to the left of A. This is what it means when I put it in the definition of a Laplace transform, which is this integral to evaluate, look at the new, because u of t minus a is 0 less than a, this integral effectively starts at a. Now I can get rid of that u. Left is this. I kind of went over that pretty quick on the previous chart. Because this cuts everything off to the left of a, the integral effectively starts at a. Now I can get rid of the unit step part. We'll do a variable substitution again. We get this, still pull out an e to the minus as, but this is actually the Laplace transform of this function, g of t plus a. So it's not quite as slick as the other one, but here's another property to put in our table. That's a little tricky. Let's do a couple examples of that. Let's say the Laplace transform of t squared cut off to the left of 2. So it's multiplied by u with the argument of t minus 2. Well, it's a here is 2, so it's e to the minus 2s. And I have to do the Laplace transform of every place there was a t in the original, I have to replace it with t plus a, and a is 2 in this case. So it's t plus 2 quantity squared. Multiply that out, I get this somewhat more complicated Laplace transform. It's not just the Laplace transform of g of t, which would have been just the t squared part. You have to go through this little bit of pain. What about this guy? Sine of t cut off to the left of pi over 2. In this case, the a is pi over 2, so I have a e to the minus pi over 2 times s, or pi minus pi s over 2. Now, every place I had t here, I replace it with plus pi over 2, t plus pi over 2. There we go. By a trig identity, that is just the cosine of t. So it becomes this, and now I can look that up in the table. Because there was a trig identity. If this were a nice pi over 2 type thing where we could use the trig identity, you just have to leave it as this sort of ugly term here. Sine of the argument of t plus whatever your a was. One last one. Original time function cut off to the left of 1. In this case, a is 1, so it's e to the minus s. The Laplace transform, every place I had a t here, I replace it with t minus t plus 1. Be careful those pluses and minuses. Even I make that mistake sometimes. So it'll be 3 times the quantity t plus 1 plus 1, which is 3t plus 4. And there we go. See how that's done? Do about one, getting a little long here. In fact, I'll do this in another recording.